Okay. Rohan, are you there?
Yes, yes.
Yeah. So, okay, so next I will introduce Rohan. He is presently pursuing bachelor's degree in information technology from our institute. He has worked on few projects that have allowed him to put what he had learned in the classroom into use in a practical sense. This year, he is a part of Google's developer club of our college, where the students learn and develop their skills. Now I will invite Mr. Rohan Rudra to carry on with his lecture. His topic of today's presentation is stereo depth estimation.
Okay. Thank you, Didi. Good evening to everyone. So today I will be presenting stereo depth estimation, and this will be an overview of my project which I have done. Okay, so what is stereo? We all are familiar with the stereo imaging capability that our eyes give us, and the same thing is done by the computers by finding the correspondences between the points that are seen by the different cameras from the different angles. So with the help of that, we are able to calculate the depth of the object from the camera, which were okay, sorry, I have not full screen. Okay, so why depth map? Measuring distance relative to vision remains difficult but absolutely key to unlocking existing applications such as autonomous driving, 3D scene reconstruction, and augmented reality. In robotics, depth is the key prerequisite to perform multiple tasks such as perception, navigation, and planning. Creating a 3D map would be another interesting application. Computing depth allows us to back project images capture from the multiple views into 3D. So that is the reason we will require the depth map. And also this is an example of the 3D reconstruction of a scene by using the number of images which are taken from various cameras from different angles. So why we are using stereo means why we are using two cameras and not any other sensors. Yes, there are other sensors also, like we know that LiDAR, which also give the similar results and also very good result actually. As you can see here, this is an image of the output of a LiDAR. But there are several advantages of LiDAR. The first one is that they are very much expensive, so that it actually makes its application less affordable. Also, in case of performance, it gets affected by bad weather conditions. Also, as it is using a laser beam and using the sonar technology to read the surroundings, so it's get disrupted by the reflections which it faces from the surroundings. So that is the reason we are shifting to cameras, as the cameras are very much cheaper than the lidars, and also with currently with the advance in computer vision and the technology, we can manipulate the images and get the more accurate and detailed results of our surroundings from using cameras. And also the cameras, this same technique are used in many electronic vehicles and even in our Mars rovers and also drones. So now let's see what is the basic idea that we'll be using. Okay, so there is an image of an ancient camera system. Here you can see that there is an object. This is a 3D object which is being presented in this wall inverted. So we can say that this is a object in the 3D space, that is it has some 3D coordinates, and this is its image which is presented in a 2D plane. That means it has two coordinates. So basically here a 3D coordinate is being transformed to a 2D coordinate. So we will be using the same principle here, that is we will reverse the logic. That is we will be using a 2D coordinate from the 2D plane of the image, then we will transfer it back to its real position, that is in the 3D coordinates in the real world. And here this is the focal length. It is from this world to this is the focal length of the camera. And this same technology, this pinhole technology, is only used in modern cameras also. but that there is a difference that nowadays here we can see that we are getting an inverted image. So basically this is corrected by rotating this along the positive z axis. Sorry. Okay, this is an image of number 8, and talking about images, that images are nothing but a matrix whose each cell contains the pixel values, or we can say that is the color values. Here, this is a grayscale image, which means that each pixel will be having only one channel, that is only one color value. So here 0 represents the darkest and 255, and more represents the white color. So here the image manipulation means we have to manipulate these matrices by mathematically. Okay, now let's move on to the theory which will be applying. So we will be using the triangulation method. Now here look at this image. Assume that we have two cameras whose image planes are exactly coplanar with each other, with exactly parallel optical axes that are known distance apart, and with the equal focal lengths, that is FL and the FR. Also assume for now that the principal points, that is CX left and the CX right, have been calibrated to have the same pixel coordinates in their respective left and the right images. Here this is the left camera space and this is the right camera space. So here the images are row aligned there, and that every pixel row of one camera aligns perfectly with the other one. We will also assume that we can find a point in the physical world P in the left and the right image views as the PL and the PR, which will have the respective horizontal coordinates as XL and the XR. This is in this simplified case, XL and XR to be horizontal positions of the points in the left and the right image allows us to show that the depth, which is here, that the Z is inversely proportional to the disparity. Disparity means the difference between the 2 points, that is the difference between XL and the XR, that is the difference between the projections from the two different cameras. So looking at the formula, you can see here that Z is the depth and XL minus XR, which are the difference between the two coordinates of the same point in the two different images from different cameras, gives us the disparity. So these two are inversely proportional. And here we have that focal length and the baseline. These two are our constants. So what is this baseline? Baseline is basically this one, that is the left and the distance between the left and the right camera, the how far distance they are put. So this T is the baseline, which will be constant. And here is the focal length. We all know focal length of the camera, so depth and disparity. So these relations gives us an idea that when the depth will be more, the disparity will be less, and when depth will be less, the disparity will be more. That means the objects which are near to the camera will give us high resolution depth images than the objects which are far away from the camera. So now to execute the previous thing, that is to calculate, to estimate the depth, we will follow this algorithm. That is, first we will take a stereo pair of images, then we will rectify them and pre-process them to improve the pixel qualities. Then we will do a block matching technique to find the similar key points and to calculate the disparity. Then we will apply it simply to the formula as we have seen earlier, that is the inversely proportional formula. Then we will visualize our outcomes. Okay, and there are two more important variables we should know. That is, one is translational vector, other is the rotational matrix. So here, suppose that this is our left camera and this is the right camera, and they are tilted a bit. And so let's assume that in this total camera system, this left camera is our origin. So for taking this as origin, the distance of this right camera, this position, this distance of this right camera is the translation, that is this one. And rotation is basically the how much the camera is tilted, how much camera is tilted will give us the R. Now there is a question may arise, why we are means why the camera are not kept parallel or they are not straight, why they are tilted a bit. This is done to reduce the field of view. As we have seen earlier from the relation, that the object near to the camera will have the more high resolution depth images. So that's why we are decreasing the field of view to get the as much as detailed information about the depth. Okay, and so now we have see what is rectification. So from the images, first we have to undistort the images, as the lens will have some tangential and radial distortions which can be removed mathematically. So after that we have to rectify. Now as we have seen earlier that we are keeping the camera frames a bit tilted, that we are rotating it. So we will rectifying it to keep the rows of each pixels parallel to each other, which will help us to find the difference between them or to apply the block matching technique. And this rectification and this distortion and to remove the distortion will be done mathematically and following a special type of geometry of stereopure, which is called the epipolar geometry, which we will not see here. Okay, now block matching technique. So this is a block. So what is block matching technique? Suppose this is our left image, this is the right image, and here suppose this is a object in our real world which is being represented here at a coordinate x0 y0. So we will move to the right image and start from this exact coordinate here, that is x0 and y0, and start searching for this exact point in this image. So we will start from right and go to the left. And why and why we are doing this, there is also a logic, and it is because of that similar epipolar geometry as I have told you. So we will start to find for it, and when we will find it, then we will take this position and we will find the difference between this coordinate and this coordinate, and the result we will get will be our disparity, that is the difference. So if we find the point here, then we will say it is a minimum disparity, and if we go to the left and then we find, then it will say it is a maximum disparity. So basically this is a block matching technique, and that semi-global block matching technique we will apply. This is it is also same, exactly same, but it has some better optimization. Okay, now see the yeah. So as I have told you that we will pre-process the images to improve its pixel properties. So as we have seen, when we take pictures, there are many situations when we get an underexposed image, or some areas are overexposed, or the contrast is not good, or the shadows are not good. So to improve those things and to make the image look sharper and more clearer, we will apply some of the methods. So methods to improve it. And here this is the histogram of the three types of the same image. Here you can see it is starting from 0 and it is going to 250, that is the pixel values here. And this is the brightest, this is the darkest area, this is the brightest part. So here you can see that the brightest parts are more higher than the brightest, and midtones are very poor. So after doing few iterations and applying some methods, we'll finally getting here a Gaussian curve where we can see that the darkest are also at a good level, also the midtones are good, and also the brights are less. So this will help us in our block matching technique. Okay, so this is our output, the depth map, and now we will visualize this. Okay, so we are using Open3D for visualization. As you can see, we are getting, we are plotting here a point cloud of every pixel. As you can see, the depth is clearly, you can see here. It is how how the objects are placed in the real world. And yes, there are few there are few problems that you can see. This can be removed by more optimization and improving the algorithm. Okay, so the future aspect, we can optimize the process and improve its speed and accuracy so that we can run on less powered CPUs and less space. We can use these different color spaces and pre-processing techniques for improving the images. Also, we can use the molecular method, which will be more effective. And another thing, this whole time we are using following only the traditional formulas and the methods. We are not going into deep learning or machine learning. and we can also use them, and they will also give us a more and more accurate results. But we are following traditional because nowadays in the electronic vehicles, or you can say in drones on any other thing, but using traditional method is a little bit of effective because they are using much less power of CPUs, so it makes it a cost effective. And these are the references which I have used. Okay, thank you. So that's all from my side.
Thank you, Rohan, for your excellent presentation.
Uh, thank you.
Now I will request Ronak to present the certificate.
Okay, thank you.
Ronak, you can stop presenting.